Hi all, welcome back. So let's continue our previous lecture. We have seen what is cut vertex. Now the next concept is, first of all, next concept is vertex cut. See, cut vertex, vertex cut. There is a difference. What is that difference? First, let's understand that difference. So let's understand this. If I give you this graph, consider this graph A, B, C, D, okay, E, F. Let's assume, consider this graph you have. Okay, now tell me, in this graph, what is a cut vertex? Cut vertex. In this cut vertex, our focus is on the vertex. Remember, our focus is on vertex. Remember this. Cut vertex. Cut vertex means our focus is on vertex. Our focus is on vertex. So I can say B is a cut vertex. I can say B is a cut vertex. I can say E is a cut vertex. Okay. So this is a cut vertex. This is a cut vertex. So you have two cut vertices. I can say that you have two cut vertices. Total two cut vertices you have. And another concept is vertex cut. Another concept is vertex cut. What is this concept? Here our focus is on cut. See, here our focus is on vertex. Cut vertex means vertex which will cut. So here our focus is on vertex. And here vertex cut. Vertex cut means here focus is on cut. Vertex cut is a set. Vertex cut is a set. Vertex cut is a set of vertices whose removal will disconnect the graph. Vertex cut is a set of vertices. For example, this set of vertices, A, D. For example, this set of vertices. Okay, so this is a set of vertices whose removal will disconnect the graph. So did you understand the difference? Please tell me. So this is a vertex cut. Here this is a cut vertex, this is a cut vertex. And here this whole thing is a vertex cut. I can say this whole thing is also a vertex cut. Okay, so I can say this is also a vertex cut. This is also a vertex cut. Is it clear? The difference, is it clear? So, okay, remember cut vertex. When you say cut vertex, then we are talking about a particular vertex. Here our focus is on a particular vertex. Vertex whose removal will disconnect the graph. And when I say vertex cut, here our focus is on the set of vertices. So this is a vertex. This is a vertex. And this is a set of vertices. This is a set of vertices. Is this clear? Please tell me, is this difference clear? Cut vertex and vertex cut. Okay. Now remember, Saurabh, see this, read this. So far, all the concepts, these concepts that we have seen, like cut vertex, this concept we have seen cut vertex. Here focus is on vertex. We have seen this concept cut edge. Here focus is on edge. So here you can notice this is a vertex which disconnects the graph. And this is an edge which disconnects the graph. Okay, which disconnects the graph. Sorry, which increases the number of, whose removal increases the number of components. Sorry, whose removal increases number of components. Whose removal increases number of components. Okay, increases number of components. So this is the definition. Please understand. So this is the definition that we have seen. Cut vertex, cut edge. Here focus is on the vertex. Here focus is on the edge. This is a particular vertex. This is an edge. Okay. And remember, these concepts, they are defined for all the graphs. These concepts are defined. We define them for all the graphs. These are defined for all graphs. For all graphs. For all undirected graphs. Disconnected or connected. For all undirected graphs, these concepts are defined. Connected or disconnected. These concepts you can define. Okay, whatever graph you have, you can define this concept for all undirected graphs. So the concept is very simple. These are defined for all undirected graph, connected or disconnected. It simply means that whose removal will increase the number of components. Just check number of components. Is number of components increasing? If number of components is increasing, then that is very good. Fine, very good. Okay. Now the next concept is actually defined for only connected graphs. These concepts, which concept? Vertex cut, edge cut. This vertex cut and edge cut. Okay, here the focus is on the cut. So here actually this is a set of vertices. Remember, this is a set of vertices, and this is set of edges, and this is set of edges. Okay, and remember, these concepts we define for only connected graphs. Because these concepts are only defined for connected graphs, so these are defined. These are defined for only connected graphs. Is it clear to everyone? Please tell me. So these concepts are only defined for connected graphs. These concepts, vertex cut and edge cut. Vertex cut means set of vertices. Edge cut means set of edges. These are only defined for connected graphs. Okay, and the definition is same. Definition is exactly same, but actually they are defined for connected graph. So the definition will become like this: set of vertices, set of edges, whose removal, what should I write? Please tell me. Whose removal disconnects the graph. Whose removal disconnects the graph. Whose removal disconnects the graph. Did you understand? Whose removal disconnects the graph. Because these concepts are only defined for connected graphs. Defined only for connected graphs. Okay. So please understand all these things. Very simple. Things are very simple. Like this is a vertex cut. Here the focus is on cut, remember. Here the focus is on cut. Okay, so vertex cut is what? Or you can call it separating set. You can call it separating set. Another name is separating set. Another name is separating set. Separating set. So this is a set of vertices. You can note this is a set of vertices whose removal will disconnect the graph. Has more than one component, means disconnect the graph. Okay, basically simply means disconnect the graph. For example, in this graph, you can notice that these red vertices, if you notice these red vertices like this D, C, E, G, I, if you consider this, like if I remove these, just think about it. If I remove these vertices, now you can notice that we got a disconnected graph. What we got? We got a disconnected graph. So tell me, what is the smallest vertex cut? Give me the smallest vertex cut. Please give me the smallest vertex cut. Is there any? Okay, the smallest vertex cut. Is there any cut vertex? Please tell me, is there any cut vertex? Do we have any cut vertex? Do we have any cut vertex? Is there any cut vertex? There is any cut vertex? Like this is not a cut vertex. This is not a cut vertex. This is not a cut vertex. So there is no cut vertex. The answer is no. So the smallest vertex cut. Okay, the smallest vertex cut. What will be the smallest vertex cut? That will be size 2. Smallest vertex cut will have size 2. Yes or no? Very simple. So what is this? So this is the idea. Now remember, smallest vertex cut. Smallest vertex cut. Smallest vertex cut. Okay, this is what? Smallest. This is the smallest vertex cut. This is the smallest vertex cut. And the size of smallest vertex cut, that is called connectivity number. Remember, size of smallest vertex cut. What is that called? Smallest vertex cut. Smallest vertex cut. Okay, is called connectivity number. Is called connectivity number. So for this graph, what is the connectivity number? For this graph, tell me the connectivity number for this graph. So because this is the smallest vertex cut, so I can say the connectivity number, and the symbol is this. The connectivity number, the symbol is kappa. This symbol is kappa. Okay, I don't know how people write it. Okay, the symbol is basically this kappa symbol. There is some symbol kappa. Okay, anyway, so you can just check how to write this symbol. Okay, so let's write it like this. Okay, so this is the symbol kappa. Okay, what we call it? We call it kappa. This is called as kappa. Okay, in Shaktiman there is a character Kapala. Okay, something like that. Have you seen Shaktiman in your childhood? So in Shaktiman there is a concept. There is a concept Kapala. Anyway, this is kappa. This is not Kapala. This is kappa. So this is the symbol connectivity number. So for this graph, what is the Kapala? What is the Kapala number? Tell me. For this graph, what is the Kapala number? The kappa number is basically 2. The connectivity number is 2. Okay. So can you notice one thing? Please notice one thing. Please notice one thing. If okay, if cut vertex exists, then what can I say? If cut vertex exists in a connected graph, because we are talking about connected graph now. Please remember, we are talking about connected graphs only now. From now onwards, we will only study connected graphs. So this point, remember, okay? Note, now onwards, study only connected graphs. Now onwards, we only consider connected graphs. We only consider connected graphs, because all these concepts like kappa, okay, consider connected graphs. All these concepts are for connected graphs. For connected graphs, we have these concepts. Remember, only for connected graphs, only for these, we have these numbers, like connectivity number. This connectivity number is defined only for connected graphs, remember. Okay, connectivity number, this kappa. This is defined for only connected graphs. Also, this vertex cut. Also, this vertex cut. Also, this edge cut. These concepts, these are defined for connected graph only. Now I am asking, if cut vertex exists, if cut vertex articulation point exists in a connected graph, then what can you say about kappa? Then what can you say about kappa? Tell me. If cut vertex exists, then the kappa will be size 1. Then kappa size will be 1. If cut vertex exists, then kappa size will be 1. Okay, very simple. Like, okay, so this is the idea. So you can notice connectivity number, that is the smallest vertex cut. Can you please tell me what connectivity number tells you? Okay, so you cannot, this is the definition of vertex cut or separating set. This is a set of vertices in a connected graph. Okay, such that G minus S has more than one component. Means, okay, this is for connected graphs. Okay, so means it will become disconnected. Now you can notice that. Please tell me what connectivity number tells you. What connectivity number tells you? Connectivity number, what this tells you? What connectivity number tells you about a graph? What connectivity number tells you about a graph? Yes, very good. Yuvraj, very good. Excellent. Yes, very good. Connectivity number tells you how difficult it is to disconnect a graph. Okay, so what this tells you? This tells you how difficult it is. So it will tell you how difficult it is to disconnect a graph. How difficult. Okay, remember how difficult it is to disconnect the graph. To disconnect the graph. So if your connectivity number is more, okay, if your connectivity number is more, connectivity number means the smallest vertex cut. If your smallest vertex cut is large, like, okay, if your smallest vertex cut that you have to remove, if that is also large, if your connectivity number is large, then it means it is very difficult to disconnect the graph. Yes or no? It is very difficult to disconnect the graph. Or I can say that it tells you, this connectivity number tells us how much connected is the graph. Tells us how much connected is the family. I can say how much connectedness is there. How much connectedness is there. How much connectedness is there. Okay, how much connected is your family? So this is the idea. Okay, how difficult it is to disconnect the graph. Like this graph, if I want to disconnect, then single vertex I cannot do. Like single vertex will not do. Single vertex will not do. I have to, okay, so these two vertices I have to remove if I want to disconnect this graph. So for this graph, the connectivity number is 2. Okay, you can note the connectivity number is 2 for this graph. And this 2 tells us that, okay, if I tell you that there is a graph, let's assume there is a graph whose connectivity number is 3, then what it means? Please tell me. Let's assume you have a graph G, connected graph. Okay, let's assume you have a connected graph G. We are talking about connected graph only. So let's assume you have a connected graph G with connectivity number 5. What this means? With connectivity number 5, what this means? Please tell me what this means. This means that any 4 vertices you remove, any, that is your choice, any 4 vertices you remove, your graph will not disconnect. Yes or no? Any 4 vertices you remove, okay, it simply means that any, that is your choice, any less than equal to 4 vertices removal, 4 vertices removal will not disconnect the graph, will not disconnect the graph, will not disconnect the graph. Okay, so like this. Okay, so minimum how many vertices you have to remove? Minimum 5 vertices you have to remove. Minimum 5 vertices we have to remove to disconnect. Okay, minimum these many vertices we have to remove to disconnect. Let's see some examples. Let's see. Tell me for path graph. Okay, like for P4, like for a tree, what is the connectivity number? Please tell me. For a tree, if you have a tree, okay, with number of vertices greater than equal to 2. Okay, number of vertices is greater than equal to number of vertices is greater than equal to 3. Let's assume number of vertices is greater than equal to 3. You have a tree with number of vertices greater than equal to 3. Then tell me what will be the kappa, this kapala, what will be the kapala of the tree? If your number of vertices is greater than equal to 3, then what is this kapala? Kappa, what is this? This is equal to 1. Okay, so you can notice tree, because tree are easy to disconnect. It simply means tree are easy to disconnect. This simply means that easy to disconnect. Tree are easy to disconnect. Trees are easy to disconnect. Very easy to disconnect them. Now let's see this complete graph. What about this K4 complete graph? What about this complete graph? So tell me, what is the connectivity number, kappa? What is the connectivity number of K4? What will be the kapala number of this K4? Okay, tell me, one vertex if I remove, will I disconnect? Please tell me. Please understand. One vertex if I remove, will I disconnect? No. Two vertex if I remove, will I disconnect? Will I disconnect? No. Three vertices I remove, will I disconnect? Will I disconnect? No. Will I disconnect? No. So let's, okay, so you can notice that what should be the answer? What do you think? What is coming to your mind? What do you think? What is coming to your mind? What should be the answer? Okay, now let me tell you, let's modify the definition. Now let's modify the definition. We will modify the definition. The kapala number is actually 3 for this. See, if you remove 3 vertices, then a single vertex will remain. A single vertex will remain. A single vertex will remain. So the kappa number is actually 3. Okay, so we need to modify our definition. The definition we have to modify. Let's modify the definition. So now this is the final definition. Okay, so this is the final definition, or I can say this is the full definition. Let's see the full definition of vertex cut. Full definition of vertex cut. Separating set. Vertex cut means separating set. Focus is on cut. Okay, full definition of vertex cut. In a connected graph, All these concepts, these are defined for connected graph, remember. So in a connected graph, what is a vertex cut? A vertex cut is a set of vertices. A vertex cut is a subset of vertices. Subset of vertices whose removal, what it will do? Whose removal either disconnects the graph, either it will disconnect the graph. Okay, please understand. Either it will disconnect the graph. Okay, either disconnects graph or single vertex remains. Or single vertex remains. Or single vertex remains. Okay, is this clear? Or single vertex remains. Either you will disconnect the graph or single vertex will remain. Is this clear? This is the complete definition. This is the full definition of vertex cut. Either you will disconnect the graph or single vertex will remain. So you can notice that for this graph, the kappa will be 3. One more thing. Remember I told you that, remember what I told you? I told you that how easy it is to disconnect a graph. This kappa tells you, you can notice this connectivity number. This connectivity number tells you how easy it is to disconnect the graph. Then for disconnected graph, if your graph is already disconnected, then what should be the kappa number? If your graph is already disconnected, if graph is already disconnected, if G is already disconnected, if G is already disconnected, then kappa number will be 0. Very good. Very good. See, if graph is already disconnected, if your graph is already disconnected, then it is okay. You don't have to put efforts to disconnect it. You don't have to put efforts. You don't have to put efforts to disconnect. Efforts to disconnect. You don't have to put efforts to disconnect. So for disconnect, okay, so for disconnected graphs, remember, if your graph is disconnected, then we define the kappa as the connectivity number is defined as 0. So the connectivity number is 0 for disconnected graph. Whatever disconnected graph you take, whatever disconnected graph you take, the kappa number will be 0. Okay, because if your graph is already disconnected, you don't have to put any efforts. There is no effort you have to put. Okay, your graph is already disconnected. You don't have to put efforts to disconnect. So I can say the connectivity number is 0. The connectivity number is 0 for disconnected graph. Okay, so this is the full definition. Means either you disconnect the graph or single vertex remains. So tell me for K6, what will be the kappa? For K6, what will be the kappa? What will be this kappa for K6? This kappa will be 5. Very good. Okay, so the kappa will be 5. Now let's see one more thing, very interesting thing. Tell me for C3, what will be the kappa? For C3, what will be kappa? Kappa will be again 2. Okay, for C3, the kappa will be 2 because you have to remove. See, if you remove this vertex, not disconnect. If you remove 2 vertices, then single vertex will remain. Okay, so now there is an interesting thing. Please tell me, for this graph, what is the kappa? K1. This is not a disconnected graph. For this graph, what is the kappa? What do you think? What is the kappa? Already single vertex is there. Yes, very good, 0. Very good, 0. Okay, so for single vertex, if you already have single vertex, then kappa is defined as 0. Okay, if you have single vertex, then kappa will be defined as 0. And for this K2, what is kappa for this K2? For this K2, what is kappa? The kappa is 1. Okay, for this K2, kappa is 1. Yes, so see, you can notice that this kappa is defined as 0 because there is no effort. Because effortless, no effort to, okay, bring single, no effort to get single vertex. No effort to get single vertex. Yes or no? No effort to get single vertex or disconnect. You don't have to put any efforts to disconnect or bring a single vertex. So very simple. So final conclusion. Okay, I hope this is the final conclusion. Remember, so here I am writing the graph, and here I am writing the kappa. Okay, the kappa number, connectivity number, the connectivity number I am writing here. So if your graph is already disconnected, if your graph is already disconnected, or your graph is single vertex, or your graph is single vertex, if your graph is already disconnected or single vertex, then kappa is defined as 0. Okay, so kappa is 0 if and only if. This is a if and only if statement. This is a if and only if statement. So your kappa is 0. Either your graph is already disconnected or you already have a single vertex. Either you already have a single vertex. See, either you already have a single vertex or you already have a disconnected graph. Okay, if you have disconnected graph, then answer will be 0. If you already have a single vertex, then answer will be 0. So this kappa is 0 if and only if your graph is disconnected or single vertex. For all other graphs, what will happen? For all other graphs, the kappa is greater than equal to 1. For all other graphs, the kappa will be greater than equal to 1. Now let's see for Kn. Please tell me for Kn now. For complete graph on n vertices. For complete graph on n vertices. So you can notice that it will be 0 for K1. It will be 0 for K1. It will be, okay, 1 for K2. And for Kn, and for K3. For K3, what is 2? So finally, I can say for Kn, it will be n minus 1. For Kn, it will be n minus 1. N is greater than equal to 2. So this is the idea. Okay, very simple. Tell me one more thing. Please understand this. Please understand the difference between cut vertex and vertex cut. Please understand this difference. Cut vertex and vertex cut. Here the focus is on vertex. Here the focus is on vertex. Here the focus is on set. Like if I give you this graph K2. In this graph K2, okay, this is your graph K2. Do we have a cut vertex? Do we have articulation point? Articulation point. Do we have articulation point? Not exist. There is no, okay, you don't have, because remember, articulation point means it should, okay, it should increase the number of components. It must increase the number of components. But do we have a vertex cut? But do we have a vertex cut? Yes. Single vertex. Okay. Do we have a vertex cut? Yes, this will be the vertex cut. This will be the vertex cut because finally single vertex will remain. This is also vertex cut. This is also vertex cut. Please tell me, did you understand the difference? Cut vertex and vertex cut. So this cut vertex is for any graph. This cut vertex, this concept is for any graph. And the definition is very simple. Okay, so this is for any graph. These are the things. So this you can define for any graph. For any undirected graph, you can define it. And how to check it? Just see if, okay, just see number of components should increase. See that number of components must increase. This is the fixed definition. Number of components must increase. Number of components must increase. Number of components must increase. And what is vertex cut? In the vertex cut, this is for disconnected graph. Okay, this is for disconnected, sorry, this vertex cut. Here the focus is on cut. This is for connected graphs. This is only for connected graphs. And the definition is what? Either disconnect the graph. Okay, see, either it disconnect the graph, either it disconnect or remains or leaves a single vertex. Either it disconnect or leaves a single vertex. Please tell me, is it clear? Please tell me. Cut vertex, vertex cut. Here the focus is on vertex. Okay. Is this clear to everyone? The difference. Let's see some more questions. For Cn, what is the kappa? What is the kappa number? Connectivity number. What is the connectivity number for Cn? For Cn, the connectivity number will be, if you have C3, then connectivity number is 2. If you have C4, then connectivity number is 2. So for any Cn, the connectivity number is 2. Whatever Cn you take. If you take this Cn, then the connectivity number is 2. If you take this Cn, then the connectivity number is 2. You can remove this A comma B. You can remove this A comma B, you can remove. This A comma B you can remove. Okay, so this is the idea. So whatever you take, here also kappa is 2, and here also this kappa is 2. Connectivity number is 2. So to disconnect a cycle graph, we need to remove two vertices. Either you disconnect the graph or leaves a single vertex. Either you disconnect the graph or you leave a single vertex. Okay, so for that we need to remove two vertices. So this is the complete idea. I hope this concept is clear. Please tell me, this is the complete concept. The connectivity number is 0 for disconnected graph. If your graph is already disconnected, then the connectivity number will be 0. Okay. And what are the one connected graph? So you can notice your graph is K connected. Your graph is K connected. If I can say your graph is K connected, if a connectivity number is greater than equal to K. Your graph is K connected if it has no, like, okay, K connected means what? Like I can say this graph is 2 connected. See, look at this. Look at this graph, A, B, C, D, and look at this graph, A, B, C. Which graph is 2 connected? What do you think? Which is 2 connected? Which graph is 2 connected? Which of these graph is 2 connected? G1 or G2? Like which is 2 connected? 2 connected means double connected. So tell me which graph is 2 connected? So this graph is 2 connected. This is not 2 connected. In this graph, if I remove this, then that's gone. So this graph is not 2 connected. This graph is 2 connected. And okay, now tell me, remember, K connected means what? What is the meaning of K connected? K connected graph. What is that? It simply means that, okay, removal of, okay, it simply means that if, okay, it simply means that kappa, the connectivity number is greater than equal to K. Okay, so the kappa is actually, this is greater than equal to K. Kappa is greater than equal to K. Okay, is this clear? Your connectivity number is greater than equal to K. Like the same idea we have seen in coloring. If you remember, the same idea we have seen in coloring. What is the meaning of K coloring? Please tell me, K colorable. What is the meaning of K colorable? K colorable, what is that? If your graph is K colorable, it means your zeta is less than equal to K. It means your zeta is less than equal to K. Yes or no? It means your chromatic number. This is the chromatic number. Your chromatic number will be less than equal to K. Very simple. Okay, similarly here, this is the connectivity number. The connectivity number is greater than equal to K. This is the connectivity number. Okay. If you say that your graph is K connected, then I can say your connectivity number is greater than equal to K. Like for example, this, okay, which graph is 2 connected? Again, next question. Which is 2 connected? Which of these graph is double connected? Like, okay, double connected. You know, there is an ad for Fevicol, Do Kadam or something. There is an ad of Fevicol. I don't remember. 2 connected. Okay. So which is 2 connected? Tell me. Can I say this graph is 2 connected? K4. Is this 2 connected? C4. Is this 2 connected? P4. Is this 2 connected? Which of these graph is 2 connected? K10, K6. Is this 2 connected? Which graph is 2 connected? Tell me. 2 connected. Yes, these graphs are 2 connected. These graphs are 2 connected. This graph is not 2 connected. Okay. Is this clear? Very simple. To K connected means simply K connected. K connected means connectivity number is greater than equal to K. This is the idea of K connected. So you can see. Okay. And if I say K connected, that simply means, if I say K connected, it simply means that K connected. It simply means that removal of any, that is your choice. Removal of any less than equal to k minus 1 vertices, removal of any less than equal to k minus 1 vertices doesn't disconnect the graph. Doesn't disconnect the graph. Doesn't disconnect the graph or leaves a single vertex. Or leaves a single vertex. So this is the idea. Doesn't disconnect the graph or leaves a single vertex. If you remove any k less than equal to k minus 1 vertices. So this is the idea of k connected. Means your graph is k connected. It means, okay, it means your chromat, it means your kappa is greater than equal to k. You have to remove, okay, you have to remove more than or equal to k vertices. You have to remove. So your connectivity number will be greater than equal to k. What is the difference between kappa and k connected? Okay, if I ask you, like this k connected and kappa, what is the difference? If I say that this is k connected, and if I say your kappa is k, what is the difference here between these two? Here I say k connected, here I say kappa is k. What is the difference? Here it simply means there is a set of k vertices. There is a set of k vertices. Yes or no? There is a set of k vertices whose removal disconnect the graph. Whose removal disconnect or leave single vertex. Disconnect or leaves a single vertex. Correct or not? Means you can definitely say that this, if your kappa is k, it means there is a set of k vertices. Definitely there is some set. There is some set of k vertices. I can say there is some set of k vertices whose removal will definitely disconnect. But here you cannot guarantee. Here you cannot say. Remember, the same statement you cannot say here. Like if I say for this same statement, you cannot say for k connected. For k connected, this statement you cannot say. This statement we cannot say. For k connected, we cannot say this statement. For k connected. For kappa equal to k, we can say this statement. This k connected simply means that your kappa, your connectivity number is greater than or equal to k. It simply means this. It does not mean kappa is equal to k. It simply means your kappa is greater than equal to k. Like in this example, see in this k6, this is 2 connected. This k6 you can notice this is 2 connected. This is 2 connected also. This is 3 connected also. This is 4 connected also. This is 5 connected also. And what is your kappa? For this, what is the connectivity number? The connectivity number is 5. So you can notice this is 2 connected, 3 connected, 4 connected, 5 connected, and finally the kappa is actually 5. This is your kappa. So when I say 2 connected, it simply means that your kappa is actually greater than equal to k 2. And yes, kappa is greater than equal to 2. Very simple. Okay, all these things are they clear? So you can notice the definition of k connected we have seen. K connected means your connectivity number is greater than equal to k. Connectivity number is the greater. And what is connectivity number? This is the smallest vertex cut. This is the smallest vertex cut. That is your connectivity number. What is the smallest vertex cut? Size of smallest vertex cut. Okay, so very simple. So this is the idea. This is the symbol kappa. And when can you say a graph is separable? A graph is separable if your connectivity number is 1. Then we will say that your graph is separable. Okay. Basically means if your graph is separable, I can say your graph is separable if vertex, if cut vertex is there. If cut vertex exists, then we will say that your graph is separable. You can separate the graph because cut vertex exists. So this is the complete idea. I hope all these concepts are clear. So these are some examples. For disconnected graph, connectivity number 0. Okay. For connected graph, connectivity number is greater than equal to 1. But remember for K1, I can say for K1 means single vertex, the connectivity number 0. For single vertex, connectivity number is 0. For single vertex. And okay, for all other vertices, for all other graph, you have 1 connected. What about cycles? Cycles of length 3, cycles of length at least 2, at least 3, that has connectivity 2. This we will see after some time. This Peterson graph, there will be a separate lecture on this. I will record. Okay, don't worry about it. This Peterson graph video I will record. This video I will record. Okay, so don't worry about it. Right now, you don't have to worry about it. Just forget about it right now. So let me remove it so that you don't have to worry about it. We will see this in a separate video. I will record it. What is the complete graph? The complete graph has connectivity number n-1. And what about the complete bipartite graph? Please tell me, what about complete bipartite graph? What is the kappa of KMN? For this, what is the kappa? For KMN, complete bipartite graph, what should be the kappa? Connectivity number. That will be, yes, very good. Minimum of m comma n. Minimum of m comma n. This will be the connectivity number. For example, if you have 2, 3, like, okay, like for example, A, B, C, D, E. This is your K23. Now you can notice that this is the K23. This is the K23. And here the kappa. If you want to disconnect this graph, then the kappa will be 2. You can remove these 2 vertices. Just remove these 2 vertices. If you remove these 2 vertices, your graph will disconnect. But remember, if you remove this vertex, then the graph will not disconnect. If you remove this vertex, graph will not disconnect. So if you remove these 2 vertices, the graph will disconnect. So I can say kappa is minimum of m comma n for complete bipartite graph. What about wheel graph? What about Wn for wheel graph? What is the kappa of wheel graph? So if you take the wheel graph, then the kappa is definitely what? Yes, kappa is 3. For this, connectivity number will be 3. Because if you notice, see, very simple. If you have this is your W3. This is the W3. Now, if I want to disconnect this, so for this, you know the kappa is 3. And let's take W4. Let's take this W4. This is W4. For this W4, how to disconnect it? See, very simple. If I want to disconnect it, then I can remove these 3 vertices. Just notice. Please notice. If I want to disconnect, I can remove these 3 vertices. I can remove. If I remove this vertex, not disconnect. If I remove this, not disconnect. But if I remove this, it will disconnect. It will disconnect. So you can notice this will disconnect. So the kappa is basically equal to 3. For wheel graph, the kappa is 3. Connectivity number is 3. So like this, all these things. And for tree, what is the kappa? For tree, kappa is equal to 1. For 3, kappa is equal to 1. But remember, if you have only one vertex, if you have only single vertex, okay, if only n equal to 1, if n equal to 1, then kappa will be 0. If n equal to 1, then the kappa will be 0. So this is how you can write the kappa. See, this is how I am writing the kappa. Okay, this is how I am writing K. This is your K and this is your kappa. So anyway. Oh, let's see. This is an interesting result and this is an important result. This is a very important result. Let's see what is this result saying. The connectivity of a connected graph is at most its minimum degree. Okay, like what this important result is saying. This is saying that if your minimum degree is 3, just let's assume, okay, this is my question. If minimum degree is 3, then what will happen? Let's assume your minimum degree is 3. Let's assume your minimum degree is 3. You have a graph, connected graph. Okay, you have a connected graph. In this connected graph, let's assume that minimum degree is 3. Then what can you say about it? What can you say about connectivity number? What can we say about connectivity number? Can you guarantee that connectivity number will be less than equal to 3? Can you guarantee this? Can you guarantee that this will be less than equal to 3? This can you guarantee? If your minimum degree is 3, then can we guarantee that kappa will be less than equal to 3? Let's see. Start with 1. If minimum degree is 1, can I say that kappa will be less than equal to 1? Start with 1. So tell me, start with 1. Start with 1. Your minimum degree is 1. Can I say your kappa will be less than equal to 1? Can I say? If the minimum degree is 1, if the minimum degree is 1, it means you have isolated vertex. You have isolated vertex, right? If your minimum degree is 1, it means what? If your minimum degree is 1, it means what? It means there is an isolated vertex. It means there is a pendant vertex. Sorry. It means there is a pendant vertex. It simply means there is a pendant vertex. You have some pendant vertex you have. So let's assume this is the pendant vertex. Let's assume this is the pendant vertex. So this has degree, this is your degree 1. Now tell me, can you guarantee? Okay, now the graph can be something like the graph. I don't know what is the graph. The graph can be anything. The graph can be anything. Now, can you guarantee? Can you give me Can you give me? Tell me. Can you say the connectivity number is what? If you want to disconnect this graph, how easy it is? If you want to disconnect this graph, just remove B. Very good, very good, very good. Okay, just remove B. If you want to disconnect this graph, just think about it. Remove B. If you remove B, then this will definitely disconnect. Okay, so to disconnect, I can say to disconnect. Either you want to disconnect, or either you disconnect or to leave one vertex, or to leave single vertex. Either you disconnect or you leave single vertex. Then what I can say, just remove B. For this, just remove B. This B you can remove. If you remove this B, then definitely what will happen? See, if you remove this B, then definitely what will happen? Either this will happen. If you remove this B, then either single vertex will remain. Either single vertex will remain. Or if you remove this B, then you will disconnect the graph. If you remove this B, then it will disconnect the graph. If you remove this B, then either it will remain the single vertex. Here you can notice single vertex you will get. Here you will get single vertex. And here you will get, if you remove B, then you will get disconnected. The same thing. Tell me here, if your minimum degree is 3, then can I say kappa is less than equal to 3? Can I say that kappa is less than equal to 3? If your minimum degree is 3, think about it. The same idea, the exactly same idea. Yes, because you have a vertex with, like, for example, this vertex has degree 3. This vertex has degree 3. Okay, this vertex has degree 3. Then if you want to disconnect this graph, okay, there can be some other graph. I don't know. The graph can have, like, okay, there can be some other graph. But you can notice one thing. What can you notice? That if I remove these 3 vertices, just think about it. This. If I remove these 3 vertices, either you will get a single vertex, or the graph will disconnect. Yes or no? Either you will get a single vertex, either this single vertex will remain, or the graph will disconnect if I remove these 3 vertices. So finally, I can say that kappa is definitely less than equal to 3. Yes or no? Is this clear to everyone? Please tell me. So if your minimum degree, if you have a connected graph, this is the final idea, that if you have a connected graph with minimum degree delta, then the kappa will be actually less than equal to delta. Your connectivity number is less than equal to delta. Okay. Yuvraj is saying, sir, if only single vertex remains, BCD are pendant. Oh, right. Single vertex will not remain because see, Yuvraj, this vertex B also has degree at least 3 because we are assuming that your minimum degree is 3. We are assuming your minimum degree is 3. It means single vertex will not remain. It means single vertex will not remain. Very simple. Single vertex will not remain definitely because this also has degree greater than equal to 3. This also has degree greater than equal to 3. This has degree greater than equal to 3. This has degree greater than equal to 3. This also has degree greater than equal to 3. So finally, I can say that if you remove these vertices, if you remove this, if you remove these vertices, definitely it will disconnect. I can say this graph will disconnect. So I can say kappa is basically less than equal to 3. So this is the final. If your graph is connected with minimum degree delta, then kappa will be less than equal to minimum degree. Kappa is always less than equal to minimum degree. And this is important. The connectivity number of a connected graph is at most its minimum degree. Okay, this is important. Please tell me, did you understand? Did you understand this? Anyone? Anyone has any doubt? So that's it. So this is your chapter. So everything we have seen, everything, every concept we have seen. Okay. So if your graph is disconnected, then your kappa will be 0. If you have a single vertex, then kappa will be 0. Okay. If your graph is complete graph, then kappa will be n minus 1. Okay. Very simple. Kappa can never be n, right? Yes or no? Some things you can notice. Tell me, is it any, okay, for any graph, can I say kappa is always, kappa is any, okay, for any graph, is it possible? Tell me. For any graph, is it possible? Tell me, is it possible? For any graph, is it possible that kappa is equal to number of vertices? That kappa is equal to number of vertices. Is it possible? The answer is no. It is not possible. The answer is no. Because see, the most connected graph, tell me one thing, the maximum kappa you can have. Who has the maximum kappa? Which graph has maximum kappa? Which graph is most connected? Remember, kappa tells you how much connected your graph is. This connectivity number tells you how much your graph is connected. Who is the most connected graph? Who is the most connected graph? The most connected graph. Who is the most connected graph? Tell me. Who is the most connected graph? The most connected graph is complete graph. That is your complete graph. And for this complete graph also, the kappa is actually what? The kappa is actually n minus 1. So for this complete graph also, the kappa is actually n minus 1. Is this clear? So you can notice, you can never have kappa equal to number of vertices. This is the most connected graph. Among all the connected graphs, if you notice, okay, consider all connected graphs. Who is the most connected? Consider all connected graphs. Consider all connected graphs. Only consider connected graphs. So if you consider all connected graphs, who is the most connected? Who is the most connected? Who is the most connected? That is your complete graph on n vertices. Okay, and who is the least connected? Who is the least connected? Least connected. That is your tree. Least connected is your tree. Are consider connected graphs, yaar. Consider all connected graphs. If you consider all connected graphs, then most connected is complete graph and the least connected is tree. Yes or no? Tree is the least connected. You already know this. This tree is the least connected graph. Okay, minimally connected. You know this, minimally connected. This tree is minimally connected. This is minimally connected. We already know this. This is minimally connected. So all these concepts we have seen. Please let me know if you have doubt. If there is any doubt, you can ask. Let's see this GATE exam question. What is the answer? GATE 1995. The minimum number of edges in a connected cyclic graph. In a connected cyclic graph. The minimum number of edges in a connected cyclic graph. You have a connected cyclic graph. So you know that if you have a connected graph, then minimum number of edges. If you have a connected graph, then number of edges is always greater than equal to n minus 1. But if you have connected graph with cycle, okay, so if you have connected graph, then number of edges will always be greater than equal to n minus 1 if your graph is connected. And if you have a cyclic graph, then number of edges will be n. This we have already seen. Okay, so very simple. Cyclic connected, I can say cyclic connected, connected also, cyclic also, connected comma cyclic, then number of edges will be greater than equal to n. And if you have acyclic connected, if your graph is acyclic connected, that is your tree, that is a tree. For that, number of edges will be n minus 1. Let's see this question. What is the answer? This is GATE 1999. How many articulation points are there? Articulation points mean cut vertices. Cut vertices. So your focus is on the vertex. Focus on the vertex. So you can notice that this 2 is an articulation point. You can notice this 2 is an articulation point. 4 is not articulation point. 1 is not articulation point. 3 is articulation point. 5 is articulation point. This is not articulation point. This is not articulation point. So finally answer will be 3. Tell me one thing. Pendant vertex. Okay, pendant vertex can be. Is it possible that pendant vertex can be cut vertex? Is it possible? Pendant vertex can be cut vertex. Is it possible? Pendant vertex can be cut vertex. The answer is no. It is not possible. Okay, because if you remove a pendant vertex, then the degree, then the number of components will not increase. So remember, cut vertex degree. What is the degree of any cut vertex? What is the degree of any cut vertex? Degree of any cut vertex. Degree of any cut vertex is greater than equal to 2. Okay, so these are some ideas. Now let's see this question. In this question, the definition is given to you. So G is a connected undirected graph. The definition of cut is given. What is this cut? This cut is set of edges. This cut is set of edges whose removal will disconnect the graph. Whose removal will disconnect the graph. So what is cut here? Please tell me. What is this cut here? Vertex cut or edge cut? What is this cut here? Cut is set of edges. So here in this question, cut is edge cut. Cut is edge cut. Yes or no? Because the question is saying cut is a set of edges whose removal will disconnect the graph. Okay. Next, the size of a cut is cardinality. Okay. Next, the min cut. Min cut is minimum cardinality edge cut. So what is min cut? That is your minimum cardinality edge cut. Edge cut is set of edges. This is, remember, edge cut is set of edges. This is set of edges whose removal will disconnect the graph. Now this graph is given to you and the question is asking, is this a edge cut? Check it out. Option A. Let's check option A. Option 1. Is this edge cut? AB, like for example, basically the question is saying that if you remove this AB, you remove this AB. Okay, I'm checking. Remember, I'm checking option A, option 1. I'm checking option 1. So if you remove this AB, let's remove this AB. Let's remove this EF. Let's remove this BD. Let's remove this AE. Let's remove this AE. Let's remove this AD. Let's remove this AD. Now tell me, did we disconnect the graph? Did we disconnect the graph? No, still not disconnected. Still not disconnected. The graph is still not disconnected. The graph is still not disconnected. Not disconnected. So this is not a edge cut. Yes or no? This is not a edge cut. What about the second option? Let's check the second option. I am checking the option number 2. This option number 2 I am checking. So you are removing BD. You are removing BD. You are removing CF. You are removing CF. And you are removing AB. You are removing AB. Now yes. Okay, now this is what you have done. So now, yes, this is the edge cut. This is disconnected. Now this graph is disconnected. So finally, this is the edge cut. Next, what is the minimum? What is the min cut? Let's see the question number B. What is the min cut? In this, do you have a cut edge? In this, do you have a cut edge? Cut edge. Do you have a cut edge? Cut edge means non-cyclic. Cut edge means non-cyclic edge. Okay, does not exist. You can notice does not exist, because every edge is cyclic edge. If you notice in this graph, every edge is cyclic edge. Every edge is cyclic edge. Every edge is cyclic edge. If you notice, every edge is cyclic edge. So in this graph, I can say that cut edge does not exist. So what is edge cut? What is edge cut? Minimum, smallest edge cut. What is the smallest edge cut? Let's see. The smallest edge cut, that will be very simple. See, smallest edge cut is actually very simple. See, very simple. If I remove, just notice, what should I do? I have three. I have three, but can I do with two? Can I do with only two? Yes, only these two. This is fine. If I do this, this is fine, right? If I do this, this is fine. This is fine. So I can say that this will be BC, CF. This will be the smallest edge cut. If I remove this one, and if I remove this one. Here actually one interesting observation you should make. Please make one observation, make one interesting observation. Very interesting observation. First of all, this is edge cut. You know what is edge cut? Here the focus is on cut. So this is set of edges. So this is set of edges whose removal disconnects the graph. Whose removal disconnects the graph. Okay, and remember, this should happen in a connected graph. In a connected graph, I can say that set of edges whose removal will disconnect the graph. This is the definition of a edge cut. You know this. Okay. Now, any graph you take, for example, A, B, C, D. Okay, let's assume this is your graph, E. Then in this graph, what is the smallest edge cut? Tell me, what is the smallest edge cut in this graph? Smallest edge cut. The smallest edge cut will, okay, like this is the smallest edge cut. I can say in this graph, the smallest edge cut is BE, DE. This is the smallest edge cut. Or I can say this is the smallest edge cut. I can also say that this is also smallest edge cut, AB, AC. Now, interesting observation. What is the, okay, what is the relationship between minimum degree and edge cut? What is the relationship between minimum degree, edge cut, smallest edge cut? Minimum degree, smallest edge cut. What is the relation between minimum degree and smallest edge cut? What is that? If your minimum degree is delta, what it means? Let's assume this vertex has minimum degree. Let us assume this vertex has minimum degree. Then if your vertex, like, okay, let's assume your vertex A has minimum degree. It means what? This is your vertex, and there are how many neighbors? How many neighbors? Total delta neighbors you have. How many total delta neighbors you have? Now you can notice one thing. This vertex A has the minimum degree delta. So you can clearly see that if I remove these edges, you can clearly see if I remove these edges, then these edges will create what? These edges will definitely create a edge cut. This is definitely edge cut. Yes or no? This is definitely edge cut. So finally, I can say that edge cut, smallest edge cut size. What can I say about this? Smallest edge cut. Remember, this is definitely edge cut. So smallest edge cut will be less than equal to delta. Smallest edge cut, that will be less than equal to delta. Okay, smallest edge cut, that will be less than equal to delta, because this is already edge cut. So the smallest edge cut will be actually less than equal to delta, because what you can do, you can remove these edges. If you remove these edges, then this vertex, your graph will disconnect. Your graph will disconnect. So finally, I can say that smallest edge cut, that is less than equal to delta. Okay, very simple. Let's see the next. In this same question, the question is asking the third part. What is the third part? Can you try this third part? Please try. Can you try this? Nikhil is asking this. So you can notice that smallest edge cut will be less than equal to delta. There are some graphs. There are some graphs for whom smallest edge cut is actually less than equal to delta. Actually, for example, you can consider a graph like this. Just consider a graph like this: A, B, C, D, E, F. Okay, so what you want? Right. Okay, E, F, G. Let's consider this graph. Let us consider this graph. So in this graph, what is the minimum degree? Nikhil, what is the minimum degree? 2, 2, 2, 3, 3, 2, 2. So now tell me, what is the smallest edge cut? What is the smallest edge cut? In this graph, what is the size of smallest edge cut? So this BE, this is the smallest edge cut. So you can notice that basically this is the idea that I can say size of smallest edge cut. So remember, size of smallest edge cut, that is less than equal to, I can say, edge connectivity. Remember, this is called edge connectivity. This is called edge connectivity. Edge connectivity. Edge connectivity. So that is less than equal to minimum degree. Okay. So please remember. So this is the definition of edge cut. We have seen the definition of edge cut. So now we are discussing edge cut. Edge cut and edge connectivity number. Edge connectivity number. Edge connectivity number. What is edge connectivity number? This is the size of smallest edge cut. Okay, so size of smallest edge cut, that is edge connectivity number. So you can notice that edge connectivity number is less than equal to delta. So here I can say that size of smallest edge cut. What is that? Size of smallest edge cut. Size of smallest edge cut, that is your edge connectivity. That is your edge connectivity number. Okay, and this edge connectivity number, this is basically less than equal to, what is the symbol for this? Let me just check, like what is the symbol for this? So let me just check. Okay, so there is a lambda. This is a symbol people use. Edge connectivity number, this lambda symbol people use. Okay, this lambda, this is less than equal to delta. Anyway, you don't have to worry about the symbol, please. Okay, one thing you should note, not all these symbols are not important. All these symbols that we have, all these symbols, like all these symbols that, for example, this is the symbol for what? Please tell me. This is the symbol for what? Omega. This is the click number. This is the click number. Okay, this is the independent set. This is the independent set. This is the edge independent set, means matching. This is the matching. This is the vertex cover. This is the edge cover. This is the chromatic number. This is the connectivity number. This is the vertex connectivity number. Okay, this is your vertex connectivity number. This is your this is your edge connectivity number. All these symbols are not important. Please understand. All these symbols will be defined, will be given to you. Will be given to you. Okay, so remember always. So these symbols you don't have to worry. These symbols will be given to you in the question. Okay, in the question it will be given to you. In the question these will be defined. These will be defined. So you don't have to worry about these symbols. Even I don't know. Like, okay, even I forgot that, okay, this is the symbol. Okay, anyway. So edge connectivity number symbol, this is the symbol lambda. Lambda is less than equal to delta. This we know. Now let's come back to this question. So in this question, you can notice that the edge connectivity number for this question. So tell me, what is that? For this question, what is the edge connectivity number for this graph? For this graph, what is the lambda? That is actually 2. Your edge connectivity number is 2, because you cannot, this is the smallest edge cut. So edge connectivity number is 2. Okay, what about this question? Question number C. Prove that in a connected undirected graph with n vertices, if you have minimum edge cut size, means your edge connectivity number is k, then these many edges you have, at least these many edges you have. This is very easy to prove. Please tell me how to prove this. Very, very, very extremely easy to prove. At least these many edges will be there. Yes, very good, very good, very good. Sort of excellent. See, this is already given to you that n vertices you have and minimum cut, minimum edge cut, basically. Okay, edge connectivity number is k. So this is saying that edge connectivity number is given to you. Okay, edge connectivity number is given to you. This edge connectivity number is already given to you as k. Okay, so this is already your k, and we already know that this k is less than equal to delta. This k must be less than equal to delta, and we know what we know. What we know? We know that n into delta is less than equal to 2e. Do we know? Do you know this? That n into delta is less than equal to 2e by handshaking, by the total degree, from the total degree. So this you already know. If you already know this, then you can notice that, and k is less than equal to delta. So I can say, finally I can say that k is less than equal to delta. So nk is less than equal to n delta, and n delta is less than equal to 2e. So I can say E is greater than equal to what? Nk divided by 2. Nk divided by 2. So very simple. So finally, this is a, if you want, this is your result. So you don't have to remember these things. You can very easily get them. So E is greater than equal to n lambda divided by 2. Will the same thing will happen for kappa? Can I say the same thing will happen for kappa? Can I say the same thing will happen for kappa? For kappa, the same thing will happen for kappa. This is the edge connectivity. You know, this is the edge connectivity number. And this is your vertex connectivity. Will this same happen? Please tell me. Please tell me, will this same happen for kappa? Yes, because we already know that kappa is also less than equal to minimum degree. Are kappa is also less than minimum degree, and this is also less than equal to minimum degree. So both are actually less than equal to minimum degree. So the same thing will happen for kappa also. So number of edges will be greater than equal to n lambda by 2, where this is edge connectivity number, and this is greater than equal to vertex connectivity. Okay, n kappa by 2. Is there any problem? Please tell me. This is your chapter. Your chapter is over. We are just taking the questions. Did you understand the chapter? Please tell me. Anyone has any doubt? Okay, Yuvraj. Yeah. Anyone has any doubt? Let me know. So the class is over now. Let's see this just one question. This question. Let's see. This is GATE 2015. What should be the answer? In connected graph, a breeze is an edge whose removal disconnect the graph. Which of the following statement is true? A tree has no breeze. Is this statement true? A tree has no breeze. No, in a tree, every edge is a breeze. In a tree, every edge is a breeze. You know this. In a tree, every edge is a breeze. What about this? A breeze cannot be part of simple cycle. A breeze cannot be part of simple cycle. Yes, breeze means non-cycle edge. Breeze means non-cycle edge. Correct or not? Why I am not getting any answer? Please tell me. Did you understand or not? All these concepts, are they clear? Every edge of a click is a breeze. No. No. A graph with bridges cannot have cycle. Again, this is no. Okay. So quite simple. What about this question? This is your GATE 2005. 20 vertices you have. Your graph has 20 vertices, 100 edges. Size of minimum vertex cover is 8. Size of minimum vertex cover is 8. Then size of maximum independent set, what that will be? Size of minimum edge cover, the minimum vertex cover is 8. Then size of maximum independent set, that will be 12. Array, we know alpha plus beta equal to n. We know this. So alpha will be equal to 12. All these things we know. We know alpha plus beta equal to n. We know alpha dash plus beta equal to n. Okay. So this is your chapter. That's it. This is over. If anyone has any doubt, you can ask. Any doubt you have, please ask. Any doubt, anyone? Saurabh is asking, for disconnected graph, we define kappa as 0. Since kappa is minimum size of vertex cut, yes, smallest vertex cut, then can we say vertex cut is null set? Yes, vertex cut is null set. Saurabh, yes, that's correct. Okay, for disconnected graph, you can say vertex cut is null set. So this is what you can say for disconnected graph. If your graph is already disconnected, for disconnected, either your graph is already disconnected or single vertex, or you have a single vertex. Okay, for disconnected or single vertex, then what can I say? I can say that your kappa is 0, and basically vertex cut. If you notice vertex cut, that will be empty. That will be empty. Any other doubt, Saurabh? Any other doubt? Hello, Nikhil.
Sir, good morning. Am I audible?
Yes. Yes, you are audible.
Sir, I have a couple of doubts. Sir, one is with the cut vertex and vertex cut. We say like in cut vertex, if like a single vertex remain, we say like in the cut vertex, मेरे को समझ नहीं आ रहा like अगर like two
हिंदी में बोल लो.
हाँ जैसे two vertices हैं path graph में K2 तो अगर उसमें हम एक वर्टेक्स को काटेंगे एक इंडिपेंडेंट वर्टेक्स बचेगा तो हम उसको कट वर्टेक्स में इंक्लूड नहीं कर रहे.
No, Nikhil. I clearly told you the definition. Just see the definition.
Yes sir, so definition के according to
What is the
vertex cut
definition
में,
of cut vertex? Please tell me. Cut vertex is a vertex. This is not a set. This
sir.
is a vertex. This is a vertex. One vertex. This is a vertex whose removal will increase number of components.
Yes sir.
Whose removal will increase number of components. Number of components must increase. Okay.
Yes
Whose
sir.
removal will increase, will definitely, okay, will definitely increase number of components. Will definitely
sir.
increase number of components. You just have to check, is number of components increasing or not? Just check that. Will increase number of components. Like if you have this graph, okay, if you have this graph, if your graph is this A, B, then there is no cut vertex here.
Yes sir.
In this, there is no articulation point. If it is confusing you, okay, then just consider articulation point. See, if this word is confusing, then use the word articulation point. Don't use this word, just use the word articulation point.
Okay sir.
This
And
word
sir,
you use, okay, articulation point. Basically, in this graph, there is no articulation point. Like B is not an articulation point because number of components is not increasing. A is not articulation point because number of components is not increasing. So there is no articulation point. But for this graph, this is the vertex cut. Here the focus is on cut. This is a set of vertices. So this is a vertex cut. This is a vertex cut. Because the definition of vertex cut says that either this is a set of vertices. Vertex cut. This is a set of vertices which will either disconnect the graph or
single
it
vertex
will leave
remain.
only one vertex. It will
Yes,
leave
sir.
only one vertex. Like see, this, if you remove this, then it will leave one vertex. Similarly, this will leave one vertex. So either you leave one vertex or you leave disconnected graph. Okay, so here you can notice for this graph G, if I ask you the kappa, means connectivity number, that will be 1. Connectivity number will be 1. This is your vertex cut. This is your vertex cut. But there is no articulation point. There is no cut vertex.
Okay.
Any other doubt?
And sir, I did not get the concept of K connected graph. Like, what was that? Like, what is K connected graph mean?
Very simple. If I give you this graph, A, B, C, D, okay. This graph, if you notice, this graph is 2 connected. If you notice, this graph is 2 connected. Why this graph is 2 connected? 2 connected means single vertex cannot disconnect it. See, single vertex cannot disconnect it. See, single vertex cannot disconnect it.
Yes, sir.
So this is 2 connected. This is 3 connected also. This is 3 connected also. Why? Because 2 vertices cannot disconnect it. See,
Yes,
3
sir.
connected means 2 vertex cannot disconnect. 2 vertex cannot disconnect. Like 2 vertex cannot disconnect. 2 vertex cannot disconnect. 2 vertex cannot disconnect. Okay. If you remove these 2 vertices, they cannot disconnect. If you remove these 2 vertices also, they cannot disconnect. So basically 2 connected. This is 2 connected also, 3 connected also. But the kappa is actually 3. But the kappa is 3. So the definition is very simple, that if you say K connected, okay, just understand the definition. K connected simply means that connectivity number is greater than equal to K. Okay, kappa is greater than equal to K. Just understand like this, that your connectivity number, your kappa is greater than equal to K. Okay.
Okay, sir. Now got it.
Like in the coloring, okay, the same concept we have seen in the coloring also. In the coloring, you know, in the coloring,
yes, sir. Chromatic number.
In the coloring, chromatic number is the smallest.
Yes, sir.
Okay. So similarly, this kappa is smallest. This kappa is the smallest. Like in the coloring, you have something called K colorable. This word you have K colorable.
Yes, sir.
This K colorable simply means that that you can do using K colors. It simply means you can do using K colors. You can do, okay, you can color using K colors. You can do color using K colors. Using K colors. But this is not minimum. Okay, if you can do using K colors, it simply means minimum will be less than equal to K. Yes or no?
Yes, sir. Minimum.
See,
ठीक है.
if you can color your house using 3 colors,
Yes, sir.
you can color your house using 3 colors. Okay, it simply means minimum how many colors you need. Minimum will be less than equal to 3. Maybe you are okay, maybe you are using one extra color, maybe you can do using 2 colors. For example, this graph A, B, C, D. This graph is 4 colorable. This graph is 4 colorable because what I can do, I can give red vertex, red, green, black, yellow. So this is 4 colorable. This is 3 colorable also.
Yes, sir.
This is 3 colorable also. What I can do for 3 colorable, what I can do, I can do yellow. If I do yellow, if instead of green, if I do yellow, then this will be 3 colorable. Sorry,
Yes, sir.
blue.
I actually like compared the K colorable and K kappa terms with the minimum, तो मैं confuse हो गया उसमें फिर. It has nothing to do with the minimum, like.
This kappa is the minimum. This kappa is the smallest. This is the smallest size. This is the smallest vertex cut.
हाँ, उससे ज़्यादा तो हो सकते हैं. Yes, sir.
This is the smallest vertex cut. Or I can say this is your connectivity number.
ठीक है. हाँ जी.
Okay.
Yes, sir. Clear, sir.
Any other doubt?
No, sir. Sir, all clear. Thank you.
Any other doubt? Anyone? Please let me know. कोई भी doubt है? Any doubt? Please let me know. So this is your chapter. Connectivity, cut vertex, vertex cut, edge cut, cut edge connectivity number, vertex connectivity number. All the points we have seen, every concept we have seen, everything, whatever we have seen in in our lecture, that is enough. We have done gate questions, everything we have done. So if you understand only this much, if you understand this completely, 100% understanding if you have for this, then you will solve every question in interview, gate exam, TIFR exam, ISRO exam, whatever exam you give, whatever interview you give, you will be able to solve all the questions. Okay. Thank you, everyone.